one, which is completely ours in one sense. That is, can you please mute?
Can we mute everyone except the speaker? Thank you.
So the third one is that through this, those who are participating here mostly are present students. So these students will know that what IUB produce, and after graduation, where you can go and what kind of knowledge you can, you can achieve through different higher studies and other things. So those who are participating here as a listener, for them, you may not understand this one. And it is very, very understandable. It's usual because it's a PhD topics. And even that for me, it's difficult to understand. For you is the same, but it's not the thing that you don't understand, so you don't listen. No, it's not the thing. The way he's presenting, the way he's delivering the knowledge, try to get that superficial understanding. That's more than enough, because that will help you to have your own interest to those fields. And if something is in your interest, then ask the question to get the way to reach to that position. Okay? So this is my suggestion from the listener, those who are present and present here to listen his speech. I'll not talk much more. I think that's all from my side. But before I go, I request Dr. Mustafa that can you do it now? That I will request everyone to open your video link, okay? So that we can take a snapshot. And that snapshot, Mustafa, you can publish in our website by highlighting our student, okay, who is giving webinar and his status. Okay?
Okay, so
can you please try, can you please open your video for a second? Everyone, please.
I think if we all mute and Naeem talks, he will become in the center. He will.
Okay, sir.
Okay, so we'll mute, okay.
Okay, sir. I'm unmuted, yes.
Okay, I got it. Thank you. All right, so thank you, Professor Mamun bin Riaz, Honorable Dean of the School of Engineering, Science and Technology of IUB, for giving us his words of wisdom. I think he said some very important points for us, our students. And so now, Naeem, the floor is yours. Please go ahead and present your keynote talk.
Thank you, sir. Okay, am I visible and audible?
Yes,
Yes,
you are
you
visible and audible. Yes, both. And your screen is visible too.
Okay, cool. All right. First of all, thank you everyone for coming in this lovely evening. And
Naeem, may I just please for a second? Sorry about this. This lecture is now being streamed live on Facebook. So for the greater audience, you can also see it from the IEEE IUB student branch website, as well as the Facebook page, as well as the EEE Department Facebook page. Sorry for interrupting you,
Department of
Naeem.
People.
Please continue.
Thank you, sir. Thank you so much. Yes, as I was saying, thank you everyone for coming and joining us today in this wonderful seminar where I'll try to share some of the research that I'm doing and some very basic ideas about what I do to my fellow younger brothers or the students who are trying to who are aspiring to come for the higher studies. I'd like to give my special thanks to our Honorable Dean, sir, and 𝐭𝐡𝐞𝐲𝐨𝐽 𝐶𝐿, Dr. 𝐭𝐡𝐞𝐲𝐨𝐽 𝐶𝐿, who is not just my academic supervisor, but also is a very close person to mine who has literally gave birth to the research entity or the research side of myself that I am actually who I am today. So I'm gonna talk about those things, but I really want to thank all of the faculty as well from my department, because I do believe that I am a product of IUB, and because of the constant guidance and the support from my faculties, I have been able to come to a prestigious PhD program in the University of Nebraska with a holding fellowship. Maybe I am the first one who got this fellowship. So I do believe it's a great honor that I had the wonderful privilege and opportunity to cross and accomplish the things that I have accomplished so far. So without further ado, let's begin. So this is a picture of the Nanoscience Center for Materials and Nanoscience in my university. So this is actually a common facility used by different departments like the Department of Chemistry, Material Science, Electrical Engineers, and many other departments. So we have a class 10 fab lab here as well. So you can see that in the clean room, I am wearing the hazmat suit, and this is inside my lab where get the this is inside my lab. So this is the NCMN, or the Nebraska Center for Materials and Nanoscience building. So before coming here, I was a student of IUB, and I graduated in 2021. And I got the admission of PhD before completing my degree, actually. And of course, I didn't have my master's, so I started directly my PhD. And while I was in my undergrad, I was heavily involved in research with Dr. 𝐭𝐡𝐞𝐲𝐨 𝐶𝐿 in the IUB-PSL, which is a lab run by Dr. 𝐭𝐡𝐞𝐲𝐨 𝐶𝐿. And there I got to know the basics of how to do research, and I was lucky to get published one journal, two journals, and about 4 to 5 conference papers. So while I was applying for my PhD, I already have 5 to 6 publications. I think that really helped me to get a good funding in my present university. And also I had an interview with my previous supervisor in the University of Nebraska, who actually left to join Penn State. And it was a remarkable experience because it was almost a 1.5 hour interview where I presented a big presentation with all my works in detail, like what I have done so far. And he was very, very impressed. So that was my career in IUB. And after that, I joined UNL. And right now I'm working with the Quantum Photonics and Phononics group, which is run by Dr. Laura Wang. She is currently the PI of our lab. Oh, so before I go to my present work, I'd like to shed a little light about what I did in my undergrad. I mean, the projects that I was involved in. So one of the project was like I worked with the nanoparticles to enhance the performance of solar cell. So what we did, we usually the plasmonic nanoparticles were used to enhance the performance of solar cell for so many years. It was nothing new. So the innovation or the nobility that we try to bring is we try to work with the core shell nanoparticle, because core shell nanoparticle has some advantages over the generic nanoparticles. Rafia, would you please mute your microphone? Thank you. Okay, so the core shell nanoparticle is actually a nanoparticle covered with a shell. So in our case, it was glass or silica. So the thing that we did is we introduced the concept of sandwich nanoparticle, as you can see here. So there's two particles. So the basic study is, the first one is just a nanoparticle placed on the top of the solar cell. On the second, we embedded the core shell nanoparticle inside the solar cell, and we could do that because the core shell nanoparticle gives the metal dielectric interface that is required to actually support the surface plasma resonance of the SPR to occur, and the core shell actually enabled us to do that. And after that, we thought, okay, so when we embed the nanoparticle inside the solar cell, and we have when we place the particle on the top, so we're getting good enhancement. Why not we combine both? And that was the birth of this sandwich configuration that we tried, and the results were pretty impressive. And secondly, in the second project, I tried to work with the morphology of the nanoparticles, where we try different shapes of nanoparticles. As we know that in the nanoscale, whenever we change the shape and the size, it varies and it affects big time. So here, as you can see, that we worked with sphere, spheroid, cuboid, cylindrical, and pyramidal shape. And at the end of the day, we also used them as a sandwich configuration to see, to tune them to our advantage. And the results were pretty impressive as well. So these were the work that I did exclusively for IBPSL, and these are included in my undergrad thesis. But on the top of that, I also got the chance to work with the University of Kentucky and Oak Ridge National Lab, where we partnered with Dr. Chris Richards, who's from University of Kentucky. So there, what we did, we worked with a zero-mode waveguide, as you can see here. So this is a aluminum zero-mode waveguide that's placed on the top of glass, and when the light was shined on the quantum dot that was placed in this cavity, or in other way you can say it as a zero-mode waveguide. So we calculated and also experimentally got some results which significantly yielded better results that can have a very positive impact for the quantum applications. So what we did is that it provided, or it showed, the photoluminescence enhancement, it suppressed the blinking, and it also improved the bi-exciton quantum yield. And these three results, as you can see in the summary, that for the enhancement of photoluminescence intensity,
Sir, can you hear me?
Yes, I can. Naeem, are you here? Okay, I think there is a technical issue. We'll try to solve this as soon as possible. Please stay tuned.
Hello, sir. Am I audible now?
Yes, you are audible.
Yes, you're audible.
Okay, I'm sorry for the interruption. Okay, let me continue
Okay.
now.
Yeah, you can present your. Okay, yeah, I can see your screen.
Okay, great. All right. So as I was saying that it really yielded some better results, which actually helped us to build different quantum technologies. This is not a paper that we work to actually directly work with something in the quantum application, but rather it facilitate the for different devices to be implemented using this idea of using the zero-mode waveguide, metallic zero-mode waveguide, uh, with the presence of different quantum dots to actually having superior results. And this was a very basic setup. As you can see that this is the aluminum zero-mode waveguide to place on the top of the glass slip. And we were the one who actually did the simulation and the calculation, and the University of Kentucky, and worked with the experimental part. And Oak Ridge National Lab actually helped to build the quantum dots and some other technical helps as well. That in the A and B, we have better biexciton. The tri-decay rate got significantly better. The photoluminescence lifetime also got better. And this is the enhancement is happening between these two. Okay, let me get this part. between the waveguides, and as you can see, the difference between the field enhancement with FDTD is pretty good. And here, as you can see, that the correlation time, the bunching and the anti-bunching is happening. So A is without the waveguide, that means just the glass that is happening in the zero. And when we see that with the presence of the zero mode waveguide, we're having quite a bit of better results. And that's followed throughout that was actually the whole paper. So this is my work while I was in my undergrad, and it would be never possible if I did not get the chance, because whenever I talk with my other friends or peers in my present university, many of them are from China, India, Pakistan, Iran, and all over the world. And none of them had this much of chance while they were undergrad. Maybe most of the research experience that they gathered while they were doing their masters or something. But during the undergrad, nobody had their research experience. The skills were pretty fundamental because undergrad is a very course intensive program, right? So we have a very less opportunity to focus on the research. But that's what I'm trying to focus, is that just because of the culture that I had in the IB PSL, I had the chance to work with big projects. Maybe that was unimaginable for an undergrad student. And for the students who are listening and who are from IB, I would say that you are very lucky. I don't know whether you realize that while you are doing the degree, but for sure, when you will graduate, you'll see that you had a lot of opportunities. Maybe you did not utilize them, but you can, because all the faculties are very helpful. If you are interested in research, talk to them, go anywhere you like. And like, if you're into power system, if you're into photonics, if you're into something else, there are different faculties who are interested in doing different kinds of research. So feel free to talk to them and see that where you find your interest, because that's very important. Do not stick to somewhere or something that you do not enjoy, because in the long run, you'll be tired and exhausted. But if you do something which you genuinely love, you'll never feel that as a burden, or you'll not feel pressurized to do that. As Steve Jobs said, like, if you are passionate about what you're doing, every day is a fun day. So I really emphasize on utilizing all the opportunities that you are having right now, and try to make a good profile, and the whole world is waiting for you. The sky is the limit. Okay, so as I was saying, that today's the agenda, the topic I was trying to talk about is quantum photonics. That's my interest, and as you can see that from the title, as you can predict, that I'm going to talk about different materials and the properties and how they can actually help to build different quantum devices. In this case, excuse me, just a second. Okay, sorry. So before that, I think many of us here who are listening to this does not have the basic understanding of quantum physics. So I would like to go through the basics very briefly so that you can have a grasp of what I'm talking about. And at the same time, I am showing the audacity to explain quantum physics in just 20 minutes. And I think it's quite funny. But again, I'll try my best, so please bear with me. I'll try to just go very briefly through the basics of quantum physics. So what is quantum physics? To put it in a very simple term, quantum physics is a fundamental physics where we deal with the matter and energy in a very, very small scale. And why it is necessary? Because the classical physics or the classical understanding of our universe does not is not applicable when we deal with the particles that are in the sub-wavelength level or very, very tiny, because particles and energy work behaves very differently, very strangely. That cannot be described with the classical physics. So that was the core idea, that why quantum physics is so important, and to know or to understand, because in the core level, that's the classical physics simply fails. So the quantum physics, the quanta, the word quanta it means, this something that's quantized, which means that it's not a continuous way of expressing something, rather it's quantized. For example, when you talk about the energy levels, it's like the first shell, second shell, right? Third, fourth. There's no 1.5 or there's no 2.5 energy level. It's quantized. And when you talk about the photon, the single photon, its photon is also quantized. That means it's a single photon. It's quantized. So that's the first basic principle of quantum physics. And so to understand that, it is inevitable to understand the Schrodinger equation, because it is very important. I know that there will be a lot of equations, but I'll try to keep it very simple. Just bear with me. It's not that complicated, trust me. So this is the Schrodinger equation in short. So as you can see that there's something H with psi, E, and psi. So H is actually an operator that we call the Hamiltonian. What is Hamiltonian? We're going to talk about that. And what is psi? Psi is the wave function. What is a wave function? Wave function is actually the function that describes the wave of any particle. And this is the Schrodinger's time-independent equation. That means the time is not applicable here. And this is the time-independent, the time-dependent Schrodinger equation. As you can see, that the introduction of T. So what's the difference between them? So the simple difference is one varies with the rate change of time and the other doesn't. For example, when we are measuring something static, for example, the energy levels, we don't need the time-dependent. The time-independent equation is just fine. But whenever we are talking about scattering, like when we want to measure the scattering of light or some particle, we need to use the time-dependent equation. So as I was saying, that Hamiltonian is an operator, which actually it means the total energy of the system. So it's the kinetic energy and the potential energy. And as you can see, when you break down, you will have something like the Planck's constant, m is the mass, that's the Laplacian, and this is the potential energy, v is potential, and psi is the wave function, as we said. So to put it in a context with the classical physics, as you can see that the H is the Hamiltonian, as we said. So the kinetic energy and the total energy makes the potential energy makes the total energy, as we already know, and that's the Hamiltonian, and E is the energy. Excuse me. Sorry for the interruption. Okay, so before I go any further, I need you to understand some quantum physics notations, or the way that the equations are usually expressed. And that is the bracket notation that was introduced by Paul Dirac. Paul Dirac was one of the godfather of quantum physics, especially the quantum electrodynamics. If you know Richard Feynman, Paul Dirac was the supervisor of Richard Feynman. So he actually introduced this bracket notation. Bracket notation is like the bra and ket. So the ket is written like this. So it's psi with this kind of symbol. So it actually means a column vector in a complex vector space. but actually a special kind of vector space that we call Hilbert space. So if you ask what is a Hilbert space, it's a special kind of complex vector space that allows that gives actually some certain categories. Like, to put it in a very simple term, all the Hilbert spaces are complex vector space, but not all the vector space is Hilbert space. In quantum physics, Hilbert space is heavily used due to some advantages. I'm not going to go into this detail. This is completely mathematical thing. So as you can see that the ket that we're talking about encapsulates the state of the quantum system, that holding information about the system properties. How? Because 𝝌, as we said, 𝝌 is the wave function, and that actually is the core of our, all the information that we have, and doing different kind of mathematical operations to the wave function, we can actually predict the future of the particle. For example, how the particle is going to behave, where it's going to go after a certain time, and lots of other things as well. So, for example, if in a two-state system in a qubit or in the quantum computer, it looks like this. So 𝝌 is actually a column vector with A and B. So that's how ket is described. Now, as I said, A and B are complex numbers, and the absolute square of these numbers is absolute A square and B square. And that represents the probability of the system being one of the two possibilities. And bra. So bra is just like that, but the symbol is a little different, as you can see. See, it's actually the conjugate transpose of the ket. So, for example, if the ket is a column vector that we just shown here, right? And the bra will be the row vector with complex conjugate elements. So we're dealing with A and B, right? So for the bra, it will be A conjugate and B conjugate. So that's ket and bra. Now, the second thing that is important is this bra ket and ket bra notations. So the first one is the inner product, bra ket. So this inner product, or another way of saying the dot product, is very important, because as we remember, we said the Hilbert space. In the Hilbert space, inner product is a must. But for the vector space, it can be inner product, it cannot be, doesn't matter. But because due to the orthogonality or the convergence and different other applications, this inner product is very, very important. So as we're saying, the inner product or the dot product of these complex vectors, or the projection, is just the ket of 𝝌 and the ket of 𝝅. So combining them, you'll get the bracket. So it measures the overlap between two states, like how the two states are actually doing in a certain time. So if the bracket is 0, that means the states are orthogonal. That means there's no overlap. It's also what's called the probability amplitude, which is related to the probability of one state transitioning to another. To put it in very simple term, probability amplitude is very important. This is not something that is real. It is an imaginary thing, the probability amplitude. But when you square it, you'll have the probability density, or so that's how we do it. Like, we cannot get physical representation of probability amplitude, but when you square it, you have that. So the outer product, as we said, the ket and bra, this is just like the same to multiply the outer product. And that operation produces a matrix result rather than a scalar one. So in the quantum mechanics, the matrix represents an operator that can transform one state to another. Now, as we have already learned what is bra, what is ket, and what is the bra ket and ket bra, now let's apply that knowledge to the Schrödinger equation. Remember the Schrödinger equation? So this is, of course, a time-dependent one because we have t in the equation. So here, as we can see, that ket represents the state of quantum system at time t. The Hamiltonian H involves the Hamiltonian operator H cap acting on the ket dictates how the state of the system evolves over time. So with this Hamiltonian, we can predict the behavior of the system. And the change in the quantum state over time scaled by the imaginary unit and the reduced Planck constant ℏ, that as you can see. Now, let's summarize. So this is the Schrodinger equation. This is time dependent or independent. This is, of course, there is no time, so it's time independent. And I have written in the bracket notation. And this is the time dependent one, right? So as I said, the H is the total energy. Remember, Hamiltonian is the total energy, that the potential and the kinetic. So it will have a kinetic term and a potential term. So this is the kinetic term. The H goes by 2m. M is the mass. H and the this is the Laplacian, the Nebula square, that represent the sum of the second partial derivatives with respect to the spatial coordinates. Spatial coordinates means like in the space, like in the over x or y coordinate, like, you know, on the space. And the potential energy term is the V, you know, any kind of potential energy is just the same. So it will be different, for example, whenever you're working with the gravitational field, and when you're working with the electromagnetic field or the EM field, of course, the potential energy will be different, but this is what it is. So now put it and summarizing it, like if we put the Hamiltonian term here, how the equation is going to look like if we replace the H here, it's going to look like this, right? So this is our Hamiltonian, and this is our, you know, 𝝌, and this is our left part of the equation. So why it is important? This was the significance. The significance is Hamiltonian is crucial because it encapsulates all the information about the dynamics of the quantum system, how its state evolves over time. And by solving the Schrodinger equation for a given Hamiltonian, one can predict the future behavior of quantum systems. So if you want to predict the behavior of an electron or a quantum dot or anything in a very, you know, in a quantum state, Schrodinger equation is like is the best tool that you have. Okay. Now we have got a basic idea about the Schrodinger equation. Let's talk about some other properties. The first I'm going to talk about is the quantum superposition. So what is superposition? Superposition is something that, like, in an overlap state. So think about this. In the classical state, if you have a ball and a box, either the ball can be outside the box or it can be inside the box. But in the quantum superposition state, the ball can be simultaneously inside and outside the box. Maybe the probability will be different, but it can be at the same time in two different places. So that is very counterintuitive if you think from a classical perspective or seeing in our world. We never see that two people are you know, present at this in two different places at the same time. But in quantum world, that is a very common phenomena. So if you think about the spin state, like, you know, either we have an up spin or a down spin, but in the quantum superposition, we can have both up and down spin at the same time. So think about this qubit, like, you know, if you think about the up spin as 1, down spin as 0. So in the superposition, it can be any number between 1 and 0. So the probability of, like, you know, it's changing, like if it's a 0.8 or 0.6, the total probability will be the same, but, you know, it can vary. So that's a principle of the superposition. And if we express it mathematically, this is the superposition we can get. The 𝝌, this is the superposition, and 𝝌1 and 𝝌2 are the two different states that will be in superposition. And C1 and C2 is a complex number representing the probability amplitudes of this. Just remember, we talked about the probability amplitude. So this is the one. So that's quantum superposition. And now let's move into the next topic, which is wave-particle duality. Well, we are kind of familiar with this experiment, but with a different setup, I guess. That's the Young's double slit experiment. So Young's double-slit experiment, in there we actually saw the wave behavior of light. Like whenever we're putting light through two slits, it creates a pattern of like bright and dark fringes. Like this pattern is unique to the wave particle. I mean, to the wave nature, right? So without the wave, you can never have these bright and dark, these fringes, because it occurs due to the interference, or maybe it's a constructive interference or a destructive interference, but this is interference, right? So this is a proof that this is a wave. And this is exactly what happens. Like if you take a double slit and bombard it with hundreds and thousands of electrons without any observation, this point to be noted, I'm going to talk about this. So without any observation, you'll have a pattern that is like bright and dark. As you can see that if you just put 40 random electrons, you will have a pattern like this. If you increase the electrons to 200, you'll have much better, bright and dark. With the 2000, it's much more evident. So you can see the intensity. It's a constructive interference, destructive, and all these things are happening. So for sure, as you can see, that electron is behaving like a wave. And that is very similar to the interference pattern of the Young's double-slit experiment. But now, let's do the same experiment, but this time we'll try to measure where this electron is going, like which slit this electron is choosing to go. And when we do that, there's something very strange happen. And the strange thing is, it becomes just a particle. It doesn't behave like wave. We don't see the fringes anymore, because whenever we are trying to measure it, we are interfering with the system. And what is happening is that, something is called decoherence. Coherence and decoherence, that's another concept. I'm not going to talk about that. But just the takeaway message is, whenever in the presence of observer that's another term that is being heavily debated, that by the observer, we do not, in the quantum physics, we do not mean that someone intelligent animal has to observe. No, it means any kind of interaction that is happening. So when the electron is going through without any kind of interruption, without any kind of interaction with any other thing, it behaves like wave. But whenever we try to measure it, we try to see where it's going, we do any sort of interfere with the system, the wave function collapses and the quantum coherence gets lost, and the wave nature turns into just a particle nature. So the idea that I'm talking about is that the de Broglie already hypothesis actually justified that even further, that not only the photon, but any particle has a wave nature. If it's tiny enough, we can actually see the coherent state, and there we can find the wave and the particle at the same time. So why this equation is so fascinating is because lambda corresponds to the wavelength and p corresponds to momentum. So momentum is something that is an intrinsic property of any kind of particle, and lambda is an intrinsic property of a wave, right? So he actually combined the particles and the wave, and for the first time in a formal way, of course. So that's the wave particle duality. Now let's talk about quantum entanglement. Well, to put it very simply, quantum entanglement means when the two particles, any two particles is entangled, if you do any kind of change to one particle, the other particle will change instantaneously. Let me explain. So what it says is, like, if you have two electrons, one electron has a spin up and another electron has it down, and they are quantumly entangled, and you take these two electrons to two different and do any kind of measurement to one, if the first one is up, the second one will be down at the same time. And this doesn't make any sense, of course. And Einstein did not agree with it either. He commented on this phenomena as like a spooky business at a distance, because he thought that this is ridiculous and totally absurd. And but hundreds of experiments, like the Bell experiment and different other experiments, have proved it over and over again, not just mathematically, but in real life. We have got proof that quantum entanglement is very true and very, very, it's as true as it can get. And with that, we have, this is actually the core the core concept for the quantum cryptocurrency, not the cryptocurrency, but the cryptography or any kind of crypto thing that is related with quantum. The quantum entanglement is the core, the theory or knowledge behind it. Also, in other words, like the teleportation, you know, the something that we used to see in the science fiction. The teleportation is actually possible, and it is happening right now. Like, we can teleport hundreds atoms or 100 or maybe 500 atoms to different places, and the quantum entanglement is a core knowledge behind this thing. And if you see it from a mathematical point of view, as you can see that the entangled wave function is not equal to the wave function of like the ket A and ket B. That means that A and cannot be factorized separately. It has to be intertwined always. So that's the meaning of entanglement. So this is, as I said, this is the properties of core of quantum teleportation and quantum cryptography. Now I'm going to talk about the uncertainty principle, which is pretty simple actually, because I think all of us have read it in our A-levels or HSC. So what it means is that the fundamental limit to the precision with which certain pairs of physical properties, such as the position and momentum, cannot be simultaneously known, which means if you try to pinpoint the position of a particle, you can never know the momentum. And if you try to know the momentum, you can never get to know the exact position of the particle. And that's what it says, like the x, and x is the space, and the p is the momentum, should be greater or equal to the ℏ2, or like the Planck's constant, reduced Planck constant over 2. So in other words, we can say that the less precisely the complementary property can be known, which means like the more precisely you're going to know the position, the less you know about the momentum, and the more you know about the momentum, the less you know about the position, or vice versa. And this is Heisenberg, who was who actually introduced the concept of the uncertainty principle. Now, another very interesting thing is quantum tunneling. So quantum tunneling means, think about this way. So if a particle is going through a barrier, in classical mechanics, it cannot go through the barrier. If the potential of the particle that is moving around, for example, it has a kinetic energy, which is E, is greater than this barrier's potential energy, it can roll over it like this. Like, you know, like if you roll a ball and the ball is having enough speed or the velocity, it can go to the slope and like cross it over. But if it doesn't, it will just rebound, right? But in quantum mechanics, what we observe is particles can go through the barriers. And that is pretty fascinating, because imagine that you can run and go through a door or a wall. And what happens here is actually, so E is actually the energy of the particle, and the V is the potential of the barrier. So E is greater than V, of course, E is moving very smoothly. But when it is less than, E is less than V, it cannot cross it over, right? Remember, if E is greater than V, it could have been gone like this. But if it's less than v, it cannot pass through. In the classical, according to the classical mechanics, it should rebound. But in quantum physics, it doesn't. What it means is that, the wave function, it gets exponential decrease inside the barrier. So it means that it gets reduced, but it's a non-zero value. That means the probability is not zero. So the probability is non-zero means there is a little chance that some of the particles will be able to pass through this barrier. So that's a quantum tunneling. And that's actually the core idea of a lot of technologies that we use today. For example, the touch screen that we use, right? So that uses the quantum tunneling technology in the diodes, or even in the cameras. The modern cameras in our smartphone also use the quantum tunneling. So the equation for the quantum tunneling looks something like this. So P is the probability, is the E, and 2K kappa. If you derive the kappa is something like this. So 2m, m is the mass, v is the potential of the barrier, E is the energy of the particle, h, the Planck's constant, and A is the thickness of the barrier. So that's quantum tunneling. As I said, so m is the mass of the particle, v is the potential, E is the energy, and A is the width of the barrier. So these are the basics of the quantum physics that you need to understand, that why quantum physics, or which properties of quantum physics we use to build different of the next generation of technologies. Okay, now we are now in a position of the second quantum revolution. What it means is that we are now at a stage where we are trying to develop different technologies based on quantum physics. So the first revolution happened when, the first introduction of the quantum physics, because when the quantum physics was introduced for the first time, because due to its absurd nature, mainstream scientists were very much, they're not a fan. Even Einstein was one of the big guys, who was not a supporter of quantum physics, though he got his Nobel Prize for this, for explaining the electromagnetic effect, but he was always against the Niels Bohr, Heisenberg, or other people who are the big advocates for the quantum physics. So the last century was more like into working with the different theories of the quantum mechanics and the first quantum revolution. But now we are standing on the second quantum revolution, where we have the theories, we have the knowledge, and this is the time to implement them and make groundbreaking technologies. For example, quantum computer, and maybe different kind of hypersensitive sensors, or quantum internet, perhaps, like quantum networks and other technologies that's gonna actually change the world forever. So one of the applications can be in the quantum sensing, that is sensing beyond the uncertainty limit. So right now our sensors have a lot of limitations, but if we can make it the quantum sensing, we can have the sensitivity that is beyond the uncertainty limit. In the quantum communication right now, data breach or hacking is one of the biggest challenges that we face in the modern times. It's going to get more and more intense, because the more we get dependent on the technology, and the perpetrator or the bad guys are becoming smarter, so they're trying and finding different ways to all our banking information, all the data, everything is now under threat. But if we have quantum networks, it will be kind of technically impossible to breach, because brute force will never be possible again, because it will take trillions of years to decode just a single code when we have quantum entangled networks. And also, as I said, quantum computer will be actually revolutionizing different things. Of course, do not get the idea that the quantum computer will replace our classical computers. No, they have different purposes. Quantum computer is not going to replace a personal computer, but it's going to be helpful to simulate and understand different things that is quite impossible for even the fastest and the best supercomputers to perform at the present times. So for all these reasons, it is important to actually prepare for this second revolution to take place. And the best or the interesting thing is we are actually not sure yet how that's going to look like, because when first the silicon was, the silicon revolution was happening, nobody knew that our technology is going to get so advanced that in our smartphone we'll have like 6 or more, 6 to 7 billions of transistors in our one single IC, right? And all the things that we're doing, our smartphone is now more powerful than the computers that were used to send to the moon, right? So it's still in a phase that we still do not know or can predict actually how it's gonna be, but everyone is having their own interpretation or ideas of how that's gonna look like. So to put it in a more concrete structure, so the idea is to have an integrated quantum systems where we'll have hybrid circuit, probably, with solid-state photonic and phononic hybrid system that's going to actually be distributed to quantum computing, quantum communication, or quantum sensing. And at the base of this, as you can see, that vertically integrated layers of technical expertise is the quantum materials. Like which materials is going to be the king, right, in the quantum technology. Different materials have different properties. Some are favorable, some are not. Some are favorable for some applications, some are favorable for other applications. But we're trying to find like a silicon, right? We're trying to find a silicon that's going to be the gold standard for most of the quantum technologies. Of course, specialized quantum technologies will always be different, but we're trying to find which one is the best. So some of the research groups are working with perovskites, some are working with silicon carbides, some are working with diamond envy center, or that is called the nitrogen vacancy. Envy means nitrogen vacancy. So diamond is made of carbons. So if you see the structure of carbons, so if you somehow remove one of the carbons, so there's a vacancy, and in the vacancy, if you enter a nitrogen, so that's the core concept of the diamond envy center. So that actually works as an electron trap, and with that electron trap, you can use it for different applications. So diamond envy center is one of the promising candidates as well. We can see the hexagonal boron nitride, TMDCs, transitional metal dichalconogides or something. So we have lots of candidates. We are still not sure which is going to be actually be the silicon. So that's the question we're asking to ourselves. And the second step is going to be these, quantum entities, which are actually going to produce the single photon or the phonon, or we have acoustic waves or spin qubits. And from the qubits, we can make some devices in a very nanoscale. For example, we can have mechanical resonators, optical cavities, or the surface acoustic wave transducers, and so on. So if you can see the vertical integration layers, at the bedrock is the quantum material. So that's what we are talking about today. So as the question I was asking, like, which material or the device system will be the silicon in the new wave of quantum revolution? Well, the first candidate is silicon carbide, because it has some favorable properties. First of all, it is a wide transparent window. So wide transparent window means like it is transparent to a wide spectrum of light, from visible to even IR, right? So that's a good advantage. Also, it provides a strong second-order optical nonlinearity. Why this nonlinearity is important, I'm going to talk about in the next slide, but this is very interesting, this nonlinear properties for the quantum applications. It has high thermal and chemical stability, which is, of course, what we want. It can host robust quantum emitters. It has good piezoelectric response, and it is silicon compatible, available for on wafer scale. Because silicon carbide is something derived from silicon, right? And already most of our technologies are silicon based. So this actually gives us a lot of in-house ready tools to actually work on. So as I was saying, the importance of the second order nonlinearity, you can see that here, the telecom 550 nanometer is very important. So that's what we're going to tune here in this case. So what it does is that, so you can see that SHG or SFG. SHG means second harmonic generation, and SFG is some frequency generation. So what is the second harmonic generation? To put it in a very, very simple term, it's like you have two photons, you combine them and make another third photon. Two photons makes it one photons with higher energy, which means it will have a lower wavelength, but with a higher frequency, right? So that's the second harmonic generation, and the some frequency generation is the same. And the DFG is the difference frequency generation, which is like so when you subtract between the frequencies. So as you can see that in the fiber optic network, we have an input and we do different kinds of manipulation with this second order nonlinearity, and we can get out of a particular wavelength what we depending on the different applications. So as I was saying, that the theoretical value for the 3C silicon carbide, 4H silicon carbide, and 6H silicon carbide is kind of different, but this is very important. So here in the silicon second order nonlinear process, as you can see here, so this is the ring resonator, where we have a ring resonator in between, and we are inputting one light, right? So we are inputting 550 nanometer. With the sum frequency generation, we are getting two different lights together, right? One 550, one 775. In the cavity QED, it's again the same, like 775 is entering, and we are getting 1110, 775 nanometer of light. In the DFG, if we just difference them, we get another one like the 550, right? The additional one. And all these things are because of the properties of the second order nonlinearity. Yeah, okay. I'm not gonna go in much detail. I don't know what's the time. Okay, I have a few 10 minutes. Okay. So as I was saying, the cavity enhanced second harmonic generation, or SHG, and the difference frequency generation, DFG, that using those properties, we can see that the frequency mismatch does change with the width of the microring resonator that we talked about. So when we increase the width of the microring, the mismatch shifts to the left or right, and we can tune that for a particular application very, very precisely. So that's one of the biggest advantage. So the conversion from telecom to visible, so we can easily do that because telecom is a 550 and the 775 is in the visible range. So the mode numbers matching, that we can do different tweaking for different applications. Actually, the work that I'm showing is one of the work of my supervisor. So she did these experiments. So this is a proposed system where we want to integrate the quantum photonic nodes and the fiber optic communication and linking them together, as you can see that. So these have a QE or a quantum emitter here, and when the laser will come. So this is our chip. So it will have these micro ridges where we theoretically calculated and got the efficiency of over 70%. And this grating actually works as a coupler, and are able to direct and couple the light from off-chip fiber into the silicon photonic circuit. So the circuit that we built was based on silicon carbide, and so that actually yielded almost 70% of the efficiency. So yeah, that's how it's gonna be the layered stacking over another. Okay, I'm not gonna go in detail. Okay, the second candidate now let's talk about is hexagonal boron nitride. So it's also an ultra wide bandgap material. So ultra wide bandgap means, like the bandgap is, when the bandgap is high enough, we have a big transparent window. So that gives us a lot of space to work with different kinds of application. It's generally atomically smooth surface, just like silicon carbide. It has high thermal and chemical stability. It has high Young's modulus and predicted piezoelectricity and low mass density. So if you see the structure, so B is the boron and it's a nitrogen. So this is how the hexagonal boron nitride atom looks like, and it goes in the lattice after lattice, and you can stack them over graphene or any other materials, and that actually with this layering combination can gives us very different application and the results output as well. Okay, so this is a kind of like a comparison table that you can see for the emission wavelength. The diamond, silicon carbide, and hydrogen hexagonal bromide HBN, you can see that the emission wavelength for diamond usually is like 575 or 635, or for silicon vacancy, it is 738 nanometer. For silicon carbide is kind of in the IR, right? But for the hexagonal boron nitride, we have sharp lines in the spectral range, which is the visible range. So again, the maximum count rate, as you can see, is also favorable. For the spectral width length, it's less than picometer. The emission lifetime, which is another parameter, emission fraction into the zero phonon line. And yeah, so these are like the different parameters. If I'm going to talk about this, it's going to take too long, so I'm not going to go in detail. But so this is the comparison, like with the other candidates, for example, silicon carbide and diamond. So put it in a summary. So hexagonal boron nitride gives the brightest quantum emitters in the room temperature, because that is very important, because most of the quantum application, as you can see, is very vulnerable. So most of them has to function in a very, very, very cold temperature, like near 0 Kelvin. But the devices that can function, the quantum devices that can function at room temperature is one of the biggest challenge. So in this case, obviously, a bright QE in the room temperature is a wonderful thing. Again, it's the highest Debye-Weller factor at room temperature, and this is the only solid-state platform exhibiting Fourier transform limited emission at room temperature. So, though in many cases, maybe hexagonal boron nitride is not the best choices because it doesn't give the best values best results in many ways, but again, it can function in the room temperature. So that's what makes it special or favorable for different applications. So as we were saying that, the cavity quantum electrodynamics model, as you can see that So, okay, so let me explain this geometry a little bit. So this is actually a ring where we are putting the hydrogen hexagonal boron nitride, and because of this spherical structure, we experience something, or we witness something that is called the whispering gallery mode. So it's actually when the light circles around over and over again. So it's more like what happens in the gallery, like in the Colosseum or a big gallery, like the sound echoes and it increases. So it's kind of the same thing that happens like when the light goes and circles over and over again. So we have this phenomenon called whispering gallery modes. So as you can see, for the lifetime emitters, the wavelength and the strong coupling can be predicted for the microticks of HBN of thickness of above 200 nanometer and the radiation limited quality factor. Okay, so as I said in the whispering gallery mode, so there's also two kinds of coupling that happens. One is strong coupling and another is the weak coupling. So in the strong coupling, it happens like when the G is much greater than the kappa and gamma, and the weak coupling happens when the G is less than kappa and gamma. And if you see the population with the over time, you'll see that the strong coupling region has big waves and it's more like sinusoidal. And the distribution image also shows the same, the strong coupling. For the weak coupling, it's inconsistent and the population is not same, and that's what happens here. And this visualization was done with actually coding, and that's a quantum toolbox offered by Python that's called QTIP. And the cavity emitter system that's described by J-Cummings Hamiltonian. So that's another kind of Hamiltonian, and this is the equation that was used to actually calculate this strong and weak coupling of HBN. Okay, so the perovskites, that this is a project that I'm currently working on. So it's now in a very fundamental stage, but again, very interesting because perovskites have the limit, has like has the potential to actually tune in and tweak with a lot of other options. So we can make different kinds of perovskites, like the combination and the possibilities are so huge. Of course, not all of the perovskites has favorable properties for a quantum application, but some of them truly and genuinely has, and they are quite promising. Of course, some of the perovskites are not that much better in terms of results if you compare with the diamond energy center or HBN or perhaps silicon carbide or something. But in general, because of this versatility and the option to layering up, you can actually make different materials out of it that can have a very precise or favorable property. For example, the conventional perovskites, that is CSP-BBr3, and if you layer it with CSP-B2BR5, so these things are interchangeable. So whenever you make the growth process happen, so with the wet chemistry, like if you combine like in the lab, like if you make the crystals, when you combine different chemicals. For example, if you want to make the CSP-BBr2, you need to have cesium, you need to have lead, and you need to have an acid that is HBr. So they have very precise measurement, and when you measure them, they will react with after the chemical reaction. You will have something like this, if you can make it right. But some of them will have different glow or edge that's not really pure, because you have produced CSP-BBr3 in the process that is not intentional. So and when you put it in the microscope, you'll have a much better idea, like how better your crystals are. So that's what I'm doing right now in the first picture that you saw me. So this was exactly what I was doing at that time, to create big good crystals of 𝐶sPb2Br5. And if we can make a large enough perovskite crystal, then we can do different kind of maybe do ellipsometry or do other kind of like surface modification or other application to analyze their properties. And in most cases, and these new materials like 𝐶sPb2Br5, you'll not get the refractive index or the detailed data about these materials like you can have, for example, for gold or silver, right? So there are a lot to explore, and that's not what we are doing. So as I was mentioning that, and A and B can be anything, like, for the perovskite, and it has a direct band gap of 2.3 electron volt. But if you layer it, for example, in 𝐶sPb2Br5, you might have a different band gap. In this case, it's 3.35 electron volt. And again, this has a strong excitonic transition explored as a tunable quantum dots for exciton polaritons, whereas it has like a white transparent window exploited as optical cavities. Like, this layering, this purple is the lead, green is cesium, and this is bromine. So as you can see that this layering actually creates different optical cavities. Remember I told about the diamond envy center? This is kind of the same scenario, but not exactly the same. But here is also we are having something that we can use it as an optical cavity or like a electron trap in a way. And whenever we have that, we can manipulate that for maybe for producing single photon, for generating single photon, or maybe for different sensing purposes, because that's going to give us a much better tool to work with different portion as well. So as I was saying, the cavity enhanced emission observed in both Fabry-Perot and nanowire cavities, as we can see here, and 𝐶sPb3 quantum dots can be generated and activated with high spatial precision using UV laser irradiation. And as you can see that the center edge is around in the visible wavelength. And okay, so here the thing that I was saying, this is a better picture to actually to show. As you can see that this one is the 𝐶sPb2Br3, these are the green ones, and 𝐶sPb2Br5, that's our desired perovskite in this case. So what happens is that, as I said, remember that we are having kind of like a optical cavity. So whenever there's a cavity, it's just like laser. What happens is light comes and goes back and forth over and over again, and the Fabry-Perot effect happens. So within this structure, like not with the help of any other device, within the material, we can create an optical cavity that can support the Fabry-Perot effect. And that's actually fascinating, and that can actually gives us to produce maybe for different lasers or other applications. As you can see that with 325 nanometer laser, we can see that the photon emission spot, like the greens, right? Greens is a bigger wavelength. So I think I'm already 34, so I'm going to wrap up. So in short, we are standing in a time where we still do not know what's gonna happen in the next 10, 20, or 30 years, but we know it for sure in the next 30 years, the way we are gonna make and create different technologies and devices, that's actually gonna reshape the future. For example, like when people were actually making the silicons or the transistors, they did not know that transistor would have the this mind-boggling applications that we are having right now is going to get this much advanced. And it was unpredictable. Right now is the same scenario. We cannot predict for sure how it's going to go, but we know it for sure that we are going to have quantum sensing. We already have quantum computer, but we're going to have much better quantum computers, much powerful, much accessible to people. And we also going to have different quantum materials which can produce different technologies, for example, in terms of different kind of sensing. The sensor is going to get like hundreds times better, perhaps in some cases. So we are kind of like standing in this junction. So as a researcher, I am privileged to witness this wonderful time where we all are trying to explore and understand different materials and how they can actually reshape our future and be the silicon of our quantum revolution. Thank you so much for your attention and time. I hope you have learned something, and if you have questions, please feel free to ask as many questions as you can. Thank you so much.
Thank you very much, Naeem, for your wonderful presentation. I think you covered a lot of topics, starting from your research here at IUB all the way to what you're doing right now. The floor is now open for questions. So I request the audience, the participants, to please come forward with questions. Don't be shy. There's nothing called a dumb question. Feel free to ask anything to our keynote speaker.
I would like to ask a question.
Yes,
Yeah,
please.
So earlier on the slides, I saw that you mentioned a piezoelectric response as a parameter for the substrate. So why are we exactly looking for that response?
Okay, so that's actually a very big question. To put it very simply, like you understand piezoelectricity, right? So it happens like when it's a kind of like intrinsic property of a material. So if the electricity properties is not favorable for our cases or applications that you're trying to find, so it might have different kinds of interruptions or interference that's not desirable. So that's why we are interested in the piezoelectricity, because we are working in a very tiny scale, and any kind of fluctuations, the quantum fluctuations or any kind of like perturbation can actually affect your device big time. That's why.
Thank you. I also have another question, actually.
Yes, please.
So I believe you have been experienced on with the wet labs, and you've done some experimentation with photonics, I assume. So my question would be like, how close are the experimentations that you've done? How close they are with the simulations, like FTDT?
I mean, are you asking like how is it? I mean, how does it feel like to do the real experiments in comparison to the FTDT or COMSOL?
Like how close they are in terms of accuracy? Like in Bangladesh, we don't have fabrication labs or anything, so we can't really compare the simulation results that we get. So how do they differ? That's
Okay. So simulation is nothing but calculation, right? So if just imagine you don't have FTDT, you don't have COMSOL, you can still get the same results because these are all based on the very fundamental equations like Maxwell equations, right? FTDT is mostly based on Maxwell's equations. So if you understand Maxwell equations and if you can put all the parameters that you are trying to simulate, you can get the same result without the computer. Maybe you'll need 1 month to do all the calculations, like pages after pages. Maybe you'll have 1,000 pages of equations. But that's it. That's pretty much it. Like whenever you're calculating the meshing and all these things, these are calculations. These are nothing else. But the problem with the simulation is that if you don't understand what you're doing, it's like you're garbage in, garbage out. I mean, these results means nothing. It only will have a significance when you'll be able to relate it with established results. So that's the one side of simulation. With the experiment is kind of like the same, because whenever you're doing for the first time, you have no reference that, yes, I have got the best result. right? Maybe you have put something wrong. Maybe maybe one of the parameters was not right. Maybe you did not tune the apparatus properly. Maybe the laser was little tilted. Maybe your focus was not that clear. There can be hundreds of things can happen in the experiment. So what we do in science is we always try to do the peer review, like maybe you get a result from your experiment. You try to make sure this result is repeatable. Like if you do the same experiment, you'll have the same result, right? If some other people from some other country do the same result, they can recreate the same result. And when you do the calculation, of course, there will be a little bit of error for well, the theoretical values with the experimental values. This is very much acceptable. But other than that, it goes hand in hand. Like in my undergrad, I was exclusively did all my research on simulation because as you said, we did not have the chance to work with experiment because we don't have the labs and stuff. Even when I started my PhD, it was the same. I started with the simulation. In my undergrad, I used FTDT. In my PhD, I use FTDT and 𝐭𝐞 at the same time. 𝐭𝐞 is a much powerful software, by the way, because you can tweak it in a very fundamental level. But recently, when I have started working with the experimental thing, it's a different world because it takes so much time to set up the experiment. It takes so much time to gather all the materials or the items that you need and then do the experiment. So yeah, it's very different. The experience is totally different. But yes, the whole idea, the concept, and the fundamental physics remains the same. I hope it answers your question.
Great. Any further questions from the audience? Please feel free to ask.
I have a few questions.
Yes, go for it. Yes.
First of all, I would like to ask whether when you do analysis with FTDT, do you happen to use open source versions, like for example, open source codes that have been developed? One example of this is MEEP, which can utilize Python, C++, or other languages to do FTDT calculations.
Yes, I did. In my undergrad, I did some of this. I got this. In fact, okay, to be more precise, I am not very good at coding. Coding is not my forte. I somehow just get the job done. So of course, I had help from different people. For example, 𝐵 bhai, who was the predecessor of my lab. So while I was doing my simulations and experiments, a lot of the codes was the codes that he used to use. So of course we tweaked them, we changed them according to our need, we tailored them. But yes, it is the original code was not written by me. Of course, just like that, when I needed to do some different calculations, for example, when I worked with University of Kentucky, when we did the calculation with the emission and the total enhancement, this is some totally new thing for us. And that time I had to open source the codes from different sources, maybe from GitHub and other places as well. So yeah, I did. I think all of the researchers do.
So even beyond ANSYS numerical, you were able to utilize these codes, open source codes from GitHub as well.
Yes.
I see. Thank you.
You can ask the community. There are different communities, people help each other. So you can, if you see in a paper, for example, this is a very good suggestions that I have learned is that like maybe you're reading a paper and you saw that some of the researchers have used a method that you do not know how to do it, but it's very familiar to you. And you think that learning this method can help your work. Maybe they have done a completely different way or for a different purpose, different application, but you know that if you could get to know this method that's going to help your research, you can just simply send them an email like, hey, I'm working on this and I read this work. Can you please help me understand how to do this or that, or do you have any suggestion for me? Most of the time, people do not say no. So it's a 90% time it's a yes. So you can also reach out to the different researchers' papers, and that's how also you make good networks.
Thank you. That was very helpful. I still have a few more questions.
Yeah, sure.
You said you were working on perovskites and overall, but are these mainly for solar cells and other
No.
photovoltaics?
No. My work with photovoltaics ended with my undergrad. So after that, I didn't have the chance to work with solar cells anymore. But, they're it's now more fundamental, actually. So I'm not really working with any kind of with a tangible device like solar cell anymore right now. But yeah, to put your question in one single sentence, yes, I'm not working with solar cells anymore, and the perovskites that I'm using is not for solar cell.
I see. So it's more of a general purpose. You're studying
It's more
phenomena.
for quantum sensing, actually. It's a different kind of device for that reason. We want to create a single photon. So this is the whole purpose of this perovskite that I'm working on, is to create single photon, like one photon at a time, one single photon. So yeah, that's nothing to do with solar cell.
I see. And I heard that a frequent problem with perovskites when it comes to solar cell use is that they're not temperature stable and they're not water resistant. Do you have to test that sort of parameters with your work as well?
Well, if it is, as I said, again, it depends on the application. For example, when you are trying to use the perovskite for the application of solar cell, your requirement, and when I'm using the perovskite for using or generating a single photon, it's going to be completely different. So the parameters that I find favorable, you might find it completely useless. So it depends on your application.
I see. I still have one to two more questions.
Yes, go ahead.
You reviewed a bunch of quantum materials, for example, nitrogen vacancy diamond, and also silicon carbide, and also cesium lead bromide. And you said these are either one of these will be the potential next silicon for a quantum revolution. But these materials are a bit rarer than silicon. Can they be as useful as silicon in these purposes, or are these suited for that purpose, or can they be as widespread in this quantum revolution?
Okay, good question. There's a correction. I never said like one of these gonna be the next big game changer material. No, these are the potential candidates. So of course, one of them can be actually the next silicon. Yes, that is totally possible. But at the same time, it's also possible maybe a new material will come and that nobody thought about, and that's gonna actually take the place of silicon. So yeah, we cannot say for sure that like from these 3 to 4 materials, maybe you're going to get one, but they are the candidates who are in the front, like who has a much more potential because a lot of study has been done on them. So that's one thing. And the second thing is that, again, as I said, like different materials has different properties, and we are not really sure yet that which going to be the best. The best is a very strong word in science. We are very scared of using the best in any kind of superlative. So we are not sure. And the question that you asked in the last part is that the availability, right? Like silicon is available everywhere. How about HBN or diamond and these kind of things? That's gonna be the last phase, like when we know for sure. For example, we know that this perovskite is gonna be the game changer. Then the challenge will come how we are gonna mass produce this perovskite in the cheapest possible way, right? For example, just think about, I think you're working with solar cells. Like solar cells were crazy expensive once upon a time. Now they're getting, cheaper and cheaper and more efficient. But if you think about to get this kind of efficiency and pricing maybe 50 years back, it was unimaginable. So the first phase is we don't care about how expensive this is going to be. We just want to know that we can work with it. And later we can develop different methods and technologies to make it cheaper. So the first priority is never to make it cheaper. The first priority is to make sure that it works.
Oh, I see.
Yeah, of course, this is something, of course, we have to consider that if it's something so rare that we cannot, that is like almost, like non-existent, we cannot work with it. But that is something of course, we care about, but that's not the first priority.
I see. Thank you, Naeem bhai. I got all the answers that I wanted.
It's a pleasure.
Great. Any more questions from our audience?
Yes, sir. I have one question. To Naeem bhai, how does IUB PSL helped you throughout your research times in IUB when you conducted so much research in your undergrad life? So how does IUB PSL helped you throughout the time?
Everything. I wrote my first research paper here. I learned how to do literature review from here. I learned how to do the commercial grade software from here. I learned how to understand scientific works and how to the scientific rigor. I knew how the process of reviewing works. I knew how to present in front of like your peers who are experts in your field, and they're going to grill you with a question, how to face that, how to, handle those kind of situations. I have learned how to actually search for your different topics and all these kind of things. Like everything that I know today, the beginning happened there. Of course, I have come a lot far from where I started, and that's how it should be. But again, the beginning was there exclusively to IUB PSL, no doubt, hands down.
And I would like to further add that this is, we are all very proud of Naeem, but he's before an alumni of our lab, he's an alumni of the department, the EEE Department of IUB. So it's not only the work he did in my lab or my research group, but all the classes he has taken, all the other faculty members who have helped him grow intellectually and develop an intellectual curiosity, scientific curiosity. So I think it's an entire package. So I think the credit goes, also main credit goes to the department and the university as a whole. And of course, our research group was something that facilitated it, but we don't exist in a vacuum. We exist within the department and the school and within IUB. So I think that's we have to focus on that as well.
Yeah, I totally agree with sir. But he asked this specific question regarding the research. So the research keyword, that goes with this.
I would like to add few more words.
Yes, sir, please.
In this. You see, a university, right? No matter it is public or private, it's the teachers who teach, right? It's all a PhD holder, those who have gone through their research, they know the academic world. No matter whether they were working afterwards or not, it doesn't matter. But they are teachers, right? They are professors. That is their, academic values they have. It's inbuilt when you have started your work. So now you may find a lot of, constraint. You may see a lot of constraint, but it doesn't mean that you will not get it. If you want, you will get it. So simply, I'll give you another way example to your supervisor as well. I took 6 people to ICTP. It's called International Center for Theoretical Physics. The day I went there, I understood this is a place, everything is free. Now you have to know how to get it. Okay? So same goes here. You just need to have patience, you need to knock, you need to push. Don't feel that, okay, they're ignoring. No, of course, I'm much more senior than you. You are my kid. So the way I ignore my son or daughter, I will ignore you. Similar way. So just accept it. And what we do as a son, we again go to the parents and ask their dad, please give, right? So at the end, we achieve that one, the things that we want. Same goes here. Everyone is busy person. Maybe that is not his, your teacher's present interest, but not force, push him, earn it, get it, whatever needed to be done in, with your politeness and everything. You understand what message I am trying to give all of you? That we are here to give you. Just only thing, you have to have patience and you have to have that will force to get things from us. Okay?
So
You
basically
see,
what
yeah.
So basically what the Mamun sir was trying to say is every time you approach the faculty members and for some reason, if you're busy, if we say no, NO means not no, it means next opportunity.
Exactly.
Get us in the next opportunity.
Exactly. You see? I'm just simply telling you. After I joined here, I came to know that it's not that easy for a student to visit the dean straightforward. Okay? So you see, maybe that was the previous person, they thought like this, because many people is disturbing. But for example, for me, I opened it. Why? Because I'm giving the opportunity to the student, but next day I can stop. But there is an incident that is possible to make the door open, right? So you have to find out all the ways to get the things done. Because at the end, you will go up, not me. So that means you are hungry. Remember that I always used to say that one. Who is hungry, me or you? If you are hungry, you will come to me 100 times. If you are not hungry, you will not come. So be hungry. Okay? Thank you.
So if I may add a little more.
Yeah.
So what I saw in my department, like if I compare myself with other, even the public, especially the public universities, I think our faculties are way more accessible. Like in the public, if you need to talk to a faculty, you need to wait, the entire process is so complicated and the culture is different, But here, I think if you go to a faculty's room and asking for a specific question, he will ever say that I don't have time, just buzz off. He might say that this is not the time, come after this time or that time. Like they are much more accessible. I think this is something like we don't get to appreciate because we are always getting this as like taken for granted. But if you look at the public university, even the BUET, I think the accessibility is one of the key advantage of the private university, especially IUB. In my department, I can say it for sure. All the faculties, at least they try to help the students in the best of their abilities. No doubt about that.
Here I'll be a little bit sarcastic, okay? I know many of you may say that Naeem Bhai, in those era it was like that. All the teachers were so friendly. No, don't tell me this one. You know why? Because class you need to hand. So on that batch, they were like 9. So that's why we are also towards to them. Okay, think like that way. So when someone is not giving, that means somehow you're not like 9 to get the things. So be much polite, be pushy, visit him on and off, make him tired so that he will give you. Okay? Hey, but don't make me tired, okay? Okay, anyway, go ahead.
We'll wrap up soon. So do we have a few final questions from the audience? I think it was quite interactive, so I'm really happy that we had a lot of questions. Any more questions, participants? Okay.
Come on, I was expecting more questions.
Yes, me too. Come on, guys.
I have a question.
Oh, there
Yeah,
we go.
don't be afraid. Just it can be a silly question. Do not think that how people will judge you. Nobody will judge you. Just ask the silliest question as you can. No problem.
So, Bhaiya, you had suggested some two-dimensional materials for like quantum applications. So, like you did a simulation study, but how hard is it to like set up a experimental validation? Like, what are the challenges you might face? Like, let's say in your perovskite study, because like I was going through some papers and I saw that like they vary the chemical potential and like for the terahertz application and vary their tunability. So I read this paper and like it's a simulation study, but when do you like translate it to, let's say, experimental study, what kind of challenges you might face, or like how do you even go setting up something like that? Like it's in the realm of, let's say, experimental physics, right? So how do you go on, you know, like setting up an experiment that is?
Okay. Um, First of all, I'm not the best person to answer that because I don't have much of experimental experience. I'm learning. I mean, I am doing experiments for I think 7 to 8 months, 1 year tops, not even a 1 year complete 1 year. So I'm not the best person to answer that first. But what I can answer from my experience is that whenever you are doing a simulation, if there's a wrong, when you press the button, it says that there's something wrong. You can immediately change that. But when in the experiment, you will get to know that you have made a screw up after 7 days. So that's very frustrating, you know. And in the experiment, everything you have to build from the scratch. For example, you are at the perovskite that you were saying, right? So you want to do one kind of like a spectroscopy or like, you know, any kind of like analysis. Like you want to see the surface, like, you know, with the atomic force microscope, AFM, with the AFM tip, you will see the surface. For the first process, you have to make the crystal. You know, for the crystal, you need all the chemicals that is required. Then you have to do them properly. It has to be uniform. It has to be in the right temperature. The vacuum should be intact. There should be no contamination. There are a lot of things can go wrong. And after like 2 to 3 days, when the crystal will starts to grow and you will have your crystal, you'll see it under the microscope, it seems it's okay. Then you'll have to take appointment for the AFM because your lab doesn't have the AFM. It's in the nanoscience center. So you have to take the appointment. You'll go there on the right time and do the experiment. And then you realize, oh, something is wrong. And your entire 10 days that you did all the things, that's gone in vain. Compared to that, simulation is much easier because in the 10 times you can run 100 simulations. You know, the trial and error is much easier with the simulation, but in the experiment is much difficult. And also, as I said, like if you, for example, the perovskite that I was making, right? So you don't have the enough expertise to make that, but some X lab has it. You have to ask the X lab that, will you give some or make some perovskite for us? We want to do this kind of analysis. So the ball is now on their court. You can never push them. You'll have to wait and wait and wait. You know, this is just 2 days work, but they took 15 days or 1 month. You can just give them soft reminders that that's it. So till the time that arrives in your hand, you cannot do anything. So it's a very, you know, like you have to have a lot of patience, actually. That's the thing. As I said to all of you, research is not a glamorous thing. It's not like vlogging. You're doing this and you get instant results tomorrow. No. Maybe you're working on something for decades after decades and you have no achievement. All the groundbreaking things that happen, maybe some happen, like for example, you know, with the graphene extraction, you can use it with the Scotch tape, the exfoliation. It's so simple, like, you know, but before that, people are thinking so complicated. You never know when's the, you know, that the epiphany will come. But this is science. Like, you have to have the resilience to keep on going, like every single movement. Like if you even make a mistake, do not think that this is a mistake. Think like, okay, now I know this is not the way to do, or this is not the path to walk. Like you learned this, like this is a wrong step. So that's also learning. So again, do not think in a very glamorous way or like you'll have overnight success. So it's a very continuous thing that you have to be consistent and resilient and keep doing, and you know, with the hope that someday it might work.
This is actually a very good point that Naeem raised, that research is not a shortcut. There's no shortcuts in research, and it requires a lot of patience. And finally, when you get the success, that's only tip of the iceberg. That success stands upon hundreds and hundreds of failures. We don't see the failures. We don't talk about the failures, but that's how you stand. So we know success stands on the shoulders of thousands of failures, and that's just the way it works. There are just so many giants who came before us who have contributed so much and suffered so much and gave up so much, and that's what makes science and even engineering and science where it is today. So that's a very good point that Naeem raised, and that's a good thing for all our students to remember, that research is a painstaking process, it's a slow process, it's a learning process, and there is no mistakes. The mistakes is just another learning experience. So that's the way you look at it. If you're trying to look at shortcut success, it's not going to happen. So that's so anyway, any further questions?
Yes, can I ask one?
Please.
Yes, please go ahead.
When you were in your undergrad, you did the research on core shell nanoparticles. There was one part of it where nanoparticle was embedded inside the substrate. I want to know how feasible it is in terms of fabrication, or does it only stay within the domain of simulation?
Very, very difficult. Very difficult. It will require some very sophisticated methods, the lithography and some other techniques. It's possible, very much possible, yes. I even with the facilities of my university, I can make the core shell and embed them. But again, like you know, when we were doing this, we were aiming for getting a viable option, or you know, or solution for mass production. Definitely you cannot mass produce with lithography. It's going to be way more expensive. Like the 5% or 10% efficiency that you are increasing with the expense of like $1 million, it's definitely not gonna work out. But again, that's the theory. Like we propose something, and maybe someone else will come forward and will find a better way to actually make the core shell embedding system process cheaper, right? So yeah, but to answer your question, it's possible, yes, but it's gonna be very expensive.
Did you try any sort of fabrication there in your university? Like
Yeah,
something that you
of course.
simulated before?
That's what I'm doing right now. But
Oh.
I did not have the chance to do the core shell nanoparticles. Okay, let me give you an idea. Experiment is crazy expensive. Like in the perovskites, everything that I used, for example, I was working with the AFM and I broke one of the tip. And the professor said nothing, but she was, you know, I saw that her face was a little pale. I was like, come on, it was just a tip. What happened? Later, I got to know that that tip costed $5,000. So you understand. So things are very expensive, and it's not like okay, I have an open lab, let's change some chemicals and make a course. It doesn't happen this way. You need to have a lot of clearance, you know. Professor has to approve, because all these things are very expensive. The equipments are using is expensive. The materials that you're using is expensive. A lot of things, and a lot of things. I mean, you are working there. You know, this is their lab, not your lab. So you are not the one who calls the shots. So yeah, I did. Of course, obviously, I did not try to make the core shell. I did not have the chance.
Thank you, Naeem. Any more further questions?
I have a question.
Okay, yeah, Asif, go ahead.
After watching your presentation, it seems to me that there is a lot of interconnection between math, then material science, optics, quantum science. So as an engineer, when you are working on a certain problem, if you do not have that kind of understanding in math or material science, how did you overcome that?
Okay, that's a good question. You know, it's 2024. So you have Google, you have ChatGPT, you have Bard, and all that learning tools that you need. Internet is getting better every single day if you want to learn something. So yeah, I'm still learning a lot of things. I know that I have a lot of weaknesses. I have a lot of lackings in so many things. For example, as a photonics researcher, I know that I should have known these things, but I know that I have very vague idea, or like, you know, I just scratched the surface. I do not have the deeper understanding that I should have. So of course, it's a continuous learning process. Every single day I'm trying to learn something. And whenever I come across a problem that requires a special set of skills. For example, I did some coding with the 𝐭𝐡𝐞𝐲𝐽. 𝐭𝐡𝐞𝐲𝐽 is the quantum simulation tool offered by IBM, where you can simulate your codes in an actual quantum computer. So for that, I had to learn the codes there. So of course I took help from Google and different websites and stuff. So with the trial and error, I somehow got the general idea so that I can work with those simulations. So yeah, it's always a learning process. And if you find it too difficult for you to learn from the online, you can ask your peers, like your lab mates or someone that you know that who has expertise. You can always ask them to teach it to you. I mean, teach them, So yeah, ask. Never feel shy. Like never feel shy to learn something. Reach out to people.
Okay, I think we have time for one more question, and then we need to wrap up. Any further questions, guys?
Assalamualaikum here.
Walaikum
Can
assalam.
you enlighten us how your journey started in IBPSL, the first stage of research?
I mean, can it be a little more specific, like how my initial research was, or like why I joined IBPSL, or like how I joined, like what's the exact question?
Your first research work.
Okay, so I was first recruited by Mustafa sir. So I had a class with him. So in the class, I interacted with him, and he thought that I might be a good candidate for his research group. So he invited me, and we had a talk, and it was very riveting. Like we enjoyed it. We talked more than 2.5 hours. We did not know that it's 2.5 hours. So he talked about the work he's working, the plasmonic particles and how they work, and how actually these things, we talked a lot. And at that time, we both knew that this is going to be a good partnership, because I was very excited to work with these things. And he was also excited and thought me to be a good potential candidate, sorry. So that time it began. And my first project was, I guess, working with the basic simulation, like how to recreate the previous work's data so that it works. And already the previous generation was working at that time, so I had the chance to learn from them firsthand. So yeah, it was great.
Okay, I think we are almost running out of time. We have a small a token of appreciation to give to Naeem. But before that, I'd like to ask our Dean, sir, do you have any last parting comments before we end the session today? Would you like to have say a few words to wrap up today's session? See here. Don't, maybe he's not here right now. Okay, I don't see him. Okay, then thank you very much, Naeem, for your wonderful presentation and all the questions you answered to our audiences.
It's a pleasure, sir. It's always a pleasure and honor.
We have a little certificate to give you, a certificate of appreciation, which we will show you right now, and then we will email it to you in your account. So let me share my screen, and let's see, where is that certificate? I've downloaded it. How do I share the screen? Okay, untitled whiteboard. I've had 1 second. Show all windows. All right, I got it. There it is. Can you see my screen?
Yes, sir.
Yeah. So thank you very much, Naeem, for everything, for taking the time out of your very busy schedule right before you leave after your wedding, and to give us 2 hours of your time, and especially to your junior students. I'm sure they learned a lot, and hopefully they were inspired by your work, and they will embark upon a good research career and help make both IUB as well as the EEE department proud of their future performances and become one of our esteemed alumni, just like you are at this point in time.
I do believe, sir, that they will be better than me. Of course, why me?
Inshallah.
Maybe I was the first, but it should not be the, the standard. The standard should be higher.
Correct, exactly. So right now, I'd like to wrap up. Before that, I want to give a little vote of thanks. First of all, I'd like to thank the Department of EEE IUB for helping us host this session, and in particular, IEEE IUB Student Branch and IEEE Photonics Society IUB chapter, who actually did most of the heavy lifting and to set up this this webinar. And also, I'd like to thank our chief guest, our Honorable Dean of the School of Engineering, Technology, and Sciences of IUB, Professor Mamoun bin Ibn Riyaz, to give us his wisdom as well as and good comments about the talk. And last but not least, of course, Mr. Nayeem Arefin. I'm sure that he will be in touch with us throughout the next few years, and we hope to have further webinars or seminars in person when, if possible, when he's here in Dhaka. And more importantly, we're also looking forward to potentially even collaborating with Naeem and his supervisor and others in future research projects. So thank you very much, Naeem, for your time. And thank you very much.
Pleasure, sir. Thank you so much for having me, and thank you everyone for being patient and listen to this perhaps very boring seminar. But thank you so much.
Quantum is always a little difficult to start with, and that's why everyone gets a little. I mean, that's why the classical physicists themselves thought, "What on earth is going on?" You know, I always say to my students, Ahmed Daro, I always say to my students that quantum mechanics is like heavy metal, and then classical metal is like, when you like classical music, when you have to go through different gharanas, train for decades to become a sitar expert, a guru, guru or ustad. But then you have, a heavy metal band that just with big hair and just like that's quantum mechanics, challenging everything that stood
for centuries.
Yes, for centuries. So
status quo, challenging the status quo.
Absolutely. And that's what it is. Yes, someone had something to say.
Sir, it's Hrifat.
Yep.
I would like to say something to Nayeem Arefin bhaiya. It was one of his webinars 2.5 years back. I attended, and that's how I got to know about the researches he conducted in IB and about IBPSL. And 2.5 years fast forward, I graduated from this department, and I also had a very good relationship with IBPSL, co-authored and authored few papers. I would like to take this moment to thank him and Mustafa sir, and let all my junior peers know that I was in your state at one point of the time. I was sitting behind the screen in one of his webinars, and that's how I started. So if you want as well, it's never too late and it's never too early. Whenever you start, that's the right time. And I personally want to thank again Mr. Nayeem Arefin bhaiya again for his speech, for taking time out of his busy schedule right after his wedding, nevertheless. And I hope to work with you and be connected to you in the future. That's all.
Thank you so much, Hrifat.
Naeem, sorry. We have some comment. We have a comment from one of our alumni as well, Mr. Abrar Jawad Haq. He wrote it in our department page. Good to see the academic stars of our department enlightening our juniors. This is a very nice opportunity for the students to educate themselves on different topics. So you've got some comments as well, some nice comments from our.
I'm kind of nervous. I mean, I don't know how to handle those kind of words. But again, thank you so much. But I will just ask you, like, pray for me. That's the only thing I ask you. And if you ever need any kind of help, I have always tried my best to help, with the best of my abilities to anyone that came to me for any kind of help. So if someone got inspired, that's the whole purpose of this webinar, that I have crossed this path and you are in the same position, maybe 2 years back or 3 years back. So you can do it as well. This is doable and you can even do better. So that is the whole purpose of today's webinar, I guess, in a sense. So thank you, Rifat, for your kind words, and please pray for me. And I do wish you all the best for your future endeavors, and I do believe that you will do amazing in your life. Thank you so much. And Abrar, thank you as well for your lovely comment.
All right, then thank you very much to all the participants. So I think we can end the session here tonight. Naeem, have a good night, and please convey my well wishes to your family, including your wife, just not your parents, everybody, your brother, your father, your mother, and your wife. And I hope you have a safe journey back to Nebraska soon.
Thank you, sir. Thank you, sir.
Travel safe. Okay then. Allah Hafiz. Good
Good night, sir.